So that's a great grand scheme. This is how course finished. And now it's like George W. Bush on his famous aircraft carrier. We won. Now we just have to mop it up. It turns out mopping up is non-trivial. So the main thing was more or less in place in the beginning of the 70s, maybe 80s. But people who derived this formula were mathematically inclined originally. And actually that doesn't even look like this. You can identify something looking back that looks somewhat like this. So they didn't actually think that you could compute with this stuff. It was just beautiful mathematics. It turns out that in chaotic systems, this is the way to compute. This is a computational scheme. This is not just a beautiful piece of mathematics. And the idea is that if I really only want to make predictions, it means I want to produce numbers. I want to tell you, the mean diffusion in some ocean which has turbulent motion is given by some number. For example, a piece of junk floats on average 50 miles per day, but it does the Brownian motion. That kind of thing can be predicted, and I'll finish, I'll use it as an application of all this technology. Transport properties can be computed using this methodology. Now, mopping up is the first thing, is that this is a beautiful formula, but it doesn't turn out to be very good in practice. And, in kind of trivial way. I mean, just that the way you actually compute eigenvalues, in practice, there are two ways. The one that seems to be most efficient, so if you click on your MATLAB and something happens, somebody's done thinking for you, what they do is they compute eigenfunctions and eigenvalues. And that seems to be numerically best, providing, system is small enough, with number of caveats. But the other way that we compute eigenvalues, we look at characteristic determinant. We did this for finite dimensional matrices, and we find zeros of that determinant. Now, there might not be the numerically most efficient way of finding the zeros, but it has advantage that everything in that calculation will be of this form, which is invariant form. So, it'll not depend. Whenever we find eigenfunctions, eigenvectors, we have to have a basis to compute. And I just happen to know that eigenfunctions in this problem are horrible. So I'm not very hopeful that this is the good way to compute them, but maybe I'm wrong. And that's about it. You would never compute eigenvalues by looking at traces. Just don't do this. Now, you'll see why is that. And you'll have a very beautiful geometrical meaning. And geometrical meaning of using determinants. Determinants will have traces appearing with minus sign. In dynamical system theory, on the right-hand side, trace means a periodic orbit. So weights of periodic orbits will show up as relative minus signs. And there is a deep reason for that. They shadow each other, and then they immensely improve convergence of the theory.